everyone. I think we'll go ahead and get started on our next Ivan workshop on NUS on solid ground. This time I'd like to turn it over to Dave Rice.
Okay, well, welcome everyone to a good set of talks on non-uniform sampling. So I'll hand things over to John for a welcome.
Well, thank you, Dave, and good morning, everyone. Good afternoon, good evening, and wherever you may be, we always have a very good international audience with us. And once again, welcome. Dave, is this workshop number 55 or
something like that? Yes.
Like age, the numbers are getting pretty high, but in the case of Ivan, those numbers are a good thing, I suppose. But anyways, once again, welcome everyone. Very important subject material today. Excellent panel of speakers, as always. MR Resources and Q1 Instruments. Very happy to continue to bring the Ivan Workshop series. I've been doing this for several years now, and we'll continue on and on into the future. Just wanted to highlight a bit about MR Resources for just a moment, if I could. Their service contract program is what I wanted to point out today. Very, very good, solid capabilities, incredible responsiveness for those of you that rely on a service contract program, maybe from other suppliers. Please do have a look. Go to the MR Resources website. They've got a multi-tier, multi-structured service contract program offering. Like I say, great responsiveness. And the prices are very realistic, very reasonable. That said, let me turn things over for a minute to our sister company, Q1 Instruments. And Don Bouchard, can you tell us about the latest and the greatest, if you would, please?
All right, thank you, John. We invite you to get to know Q1. Q1 manufactures complete systems from 400 to 600 megahertz. We also upgrade existing systems from 300 to 600 megahertz with full automation, including a smart tune and match auto tuning probe, 24 60 position sample changer, and a 2-channel Quantum One Plus console. It's all excellent performance at an unbeatable price, and we invite you to contact us to get to know more. Thank you.
Thank you, Don. As Don mentioned, a very good, very capable lineup. Have a look at the website when you get a chance. Q1NMR, letter Q, O-N-E, NMR.com. Have a look. Anyways, all that said, Krish, could I pass it to you for just a moment? And maybe you can give us a few thoughts on upcoming meetings, if you would, please.
Thank you, John. Hello, everyone. I just wanted to talk about what is coming down the pike in Ivan workshops. After today's on NUS, on uniform sampling, next month, that's July 27th, I will be giving a workshop on time domain analysis, back to basics. And Dave Russell at Genentech agreed to be a moderator of the discussion and moderator of me. Beyond that, in August and September, we have been discussing a few topics, and it is not yet finalized, but it should be finalized very soon. As usual, we are looking at the last Thursdays of the month. So look forward to email an announcement on that. With that, I will pass it back to Dave Rice.
Okay.
Thanks.
Okay, thanks, Krish. And so our panel leaders today are Frank and Dave, and I think Dave is going to do the lead off. So let me turn things over to him.
So first of all, it's been wonderful as always to work with Frank on this, and Frank and I would really like to welcome all of you to this next session, NUS on solid ground. First, we would also, of course, like to join in the thanks to MRR and Q1 for supporting these fantastic events that bring the international community together and allow us to have these great discussions. Thanks to the Ivan Group, Chris and everyone else. and all of the David R's who are in the NMR community. It's great to be here with you to share some NUS. Very briefly, what we're going to do is we're going to start off, I'm going to do a quick tutorial, very fast glossary of NUS. The primary goal is to help set up our subsequent speakers so that they don't have to do as much background material. I have a subversive goal that it's going to help show just how established and mature the field of NUS is. But then following that, you're going to see all the wonderful research frontiers in NUS. And we're going to let some wonderful guests. That includes, first of all, Frank is also going to give us a great presentation. We're also going to hear from Ben Harding and Chad Rienstra from the University of Wisconsin. And we're going to hear from Len Mueller from University of California Riverside. And we're so grateful to them that they could join us. This is a dream panel, and we couldn't be more thrilled to have them all here. So I think with that, I think I've gone through my quick checklist. I'm going to jump in and give us a quick sort of glossary and tutorial to put us on the same page in NUS. And I call this NUS in 5 minutes, but it may be closer to 7. This is intended to be a fairly fast review. My kids would call this a speed run, where we're just going to go through some fundamental concepts and terminologies and disclaimers. A few disclaimers. This is incomplete. If something's missing, blame my head, not my heart. Just trying to get through some of the quick foundations here briefly. Terms and definitions to NUS, the other disclaimer, are not undertaken by standards bodies, but maybe they will be one day. And if you're curious, some of the figures that I'll use to illustrate these concepts are pulled from some recent works. So let's dive right in. I'm going to start with a few assumptions that I think are very safe for this audience, so I won't belabor them. Our speakers today will certainly be counting on both the classical and quantum pictures of NMR, indirect evolutions, periods, indirect frequency labeling, and so on. And our first acronym, uniform sampling, is frequently abbreviated as US. Okay. And I'm sorry for the wordiness. I understand this is being recorded. You're more than welcome to come back and read a little more slowly at your leisure. We depend in traditional NMR on the Fourier transform. A few of the beautiful theorems that decorate the Fourier transform include Parseval's theorem, which is just that the FT is power conserving. So it means what we get out of it is exactly what we put into it. We depend on things like convolution and Nyquist theorem to explain key spectral properties. The FT is, of course, linear, illustrated in this nice cartoon. You can find many variations of this online. The linearity is often, I think, undersold. We all take it for granted. It's a beautiful part of the FT. The FT is robust to time shifts, and there's more, but these are some of the highlights. Few things that all of us, I think, tend to internalize about the Fourier transform are some key Fourier pairs. We know the exponential decay transforms in principle to a Lorentzian line shape, although that's not necessarily what you may see in practical NMR. We know in particular that the Fourier transform delivers spectra to us that are amplitude-based, and we take advantage of that in many ways. It's really the natural way in which I think most of us are accustomed to looking at NMR spectra. We use amplitude, not power. And so that leads to things like an amplitude-based definition of the signal-to-noise ratio, the peak height over the RMS noise. There are a couple of common rules of thumb that people enjoy. The peak amplitude in the frequency domain is the signal envelope in the time domain. The peak area in the frequency domain is actually given by the first point in the time domain. Remarkable results. So these are some of the Fourier concepts that I think we're mostly all familiar with. Just want to run through them very briefly. So what's non-uniform sampling? So in non-uniform sampling, let me move something to the side on my own screen, pardon me. Okay. Non-uniform sampling means that we, well, it can mean a lot of things, but one of the most conventional applications is to start with the uniformly sampled grid of regularly spaced time points. And a frequent term that you'll hear, I'm sure you'll hear this again today, is the Nyquist grid. And we need to define a sampling schedule. And in this particular cartoon, you'll see that the sampling schedule is derived from the Nyquist grid. And that's an important term. We call that on-grid NUS. By the way, although it was in popular use for a long time, there's a deprecated term. Nonlinear sampling is generally no longer used. We can do NUS in a variety of dimensions. For example, 1D NUS of 2D NMR would use a one-dimensional sampling schedule. 2D NUS of 3D NMR would use a two-dimensional sampling schedule. And you can go as far as you want. In principle, here's a case that I borrowed from one of Mehdi Mobley's papers of a 3D sampling cube for 40 NMR. And indeed, there are applications in higher dimensional NMR as well. So this is some of the ways that NUS can help us get to higher dimensions. It's worth pointing out a couple of terms at this point. We use a probability density function to describe how we're going to select samples. There are a variety of ways of selecting samples. I won't get into all of them, but most people have heard of Poisson gap, for example. We also offer some schedulers that we call QSCHED. And you can see that the probability density function prescribes how we're going to choose those time points. A useful term that's seen wider adoption, I think I borrowed this term also from the Yukon group. I hope I have that attribution correct, is coverage, sometimes also called sparsity. We usually do it as a percentage. So for example, if you're sampling 8 out of 32 points, we would call that 25% coverage. Now, we have to be careful about the concept of coverage. It only tells us the percentage. Coverage does not necessarily tell us about the number of underlying data points. And so that topic will come up later. NUS in the spectral window is a fascinating concept. The general symptom is that aliasing could occur within the spectral window. And we have an example that we like to show people of a purposefully bad NUS. And by the way, I just want to assure people who are seeing this, this is not meant to be a ding on NUS. Rather, this is a purposefully bad NUS to illustrate the problem, showing very familiar HSQC to most of us. That we have a beautifully aliased at half the spectral window set of signals of our authentic peaks. There's a beautiful rule about aliasing that the upper limit of the spectral window is given by the greatest common denominator. And in fact, something that has been explored and I think deserves more attention is to see how much we can push this for extreme spectral windows. But I just want to assure people about the bottom line. If you're relatively non-sparse, your spectral window is closely approximated by the Nyquist grid. Having said that, if you're wondering where a lot of people are at right now, a lot of people are thinking about sparser NUS, and then you do need to address aliasing artifacts, and there are a variety of different approaches. I illustrated one over here, the partial component sampling, a variety of different people tackling this from different points of view. There's a variation called non-uniform weighted sampling. Here, all of the samples on the Nyquist grid are taken. However, different numbers of transients are acquired at each position on the Nyquist grid. And this is the original figure from, I think, one of the earliest papers to explore this by Kumar et al. And then some variations include here's straight NUS, here's straight NUWS. You could even combine them. So there are different variations. There's continued interest, and I think we're going to hear more about that today from one of our speakers. So why NUS? You can shorten acquisitions. You can improve resolution, and something that comes up also is improved sensitivity, where we eventually decided to write down a theorem for this, which both explains and protects that you can actually get true sensitivity enhancements, but they can be modest, so be aware of that. Few things we would want to show. This is what we would call on-grid weighted NUS, so weighted to early times. Okay, we can also do on-grid unweighted, where they're now evenly distributed. This is less common, but still used in some applications, certainly. One problem about uniform sampling that deserves mentioning is just how wasteful uniform sampling is. Really beautiful result that, to the best of my knowledge, goes back to Jerry Mattson in 1977, who derived this, oops, my 1.26T2 shifted there, the 1.26T2 maximum of uniform sampling, which really shows just how wasteful uniform sampling is, and it's one of the many reasons for NUS. Some of the ways that you can produce a spectrum. I won't get into this. I think we're going to hear more about this from one of our speakers today. But how do you take a list of non-uniform samples and turn it into spectral information? You can do this by frequency domain analyses, such as compressed sensing and IST, or time domain analyses, such as CRAFT and SMILE, and some of the theoretical foundations can be found in these references. By the way, I'd just like to point out the Fourier transform is usually at the heart of many of these methods. It's not that the Fourier transform is completely abandoned. It's no longer the sole part of the processing. It's still a part of these methods. And that's why many of these methods can be so robust, because in part, they are incorporating the Fourier transform. Some common issues that come up, you may see sampling artifacts. something that we and many others are interested in. Here's an example from our own recent works, but again, many people are approaching this from many points of view. But overall, many assurances about sampling artifacts. In conservative NUS, you may not see them. For high signal to noise, you probably won't see them. They're often comparable to thermal noise. So as long as you're using NUS in a fairly conservative regime, you're not likely to run into concerns with these. We've already addressed aliasing. Yes, NUS can in principle be used for quantitative work, but with great care, and you would need to definitely work on an SOP for that. Some folks feel a little uncertain about the sensitivity improvement by NUS. While it's a formal sensitivity enhancement, there are certainly misconceptions. It's certainly possible. It can be very small, or it can be up to a factor of 2. It can vary on your particular application. Are line shapes changed by NUS? Generally not in conservative practice, but certainly in more aggressive uses, you could see changes. Here's an example from a recent paper where line shapes were unchanged, even in a semi-aggressive use of NUS. But also recall, many people use NUS to drastically increase resolution. And so, any modest broadening is more than offset by the drastic improvement in resolution. Is there a minimum number of samples? I can't wait to defer that question to somebody who's more qualified to talk about it. So I'll let that come up later. So to wrap up, maybe you're using NUS for sensitivity, maybe you're using it for resolution. Whatever you're using NUS for, my one advice for anybody getting started is be explicit and think ahead of time of what you want NUS to do for you. Are you going after time, resolution, or sensitivity, or maybe even you're getting greedy and you want to do maybe 2 of those? Be explicit. Don't just say, I think I'll try it. Know ahead of time what you want NUS to do for you. Start conservatively, start with 50% coverages. We recently developed a set of one-click quantile schedules that you can try. There's also a rich choice of Poisson gap schedules you can try. And don't be afraid to try different methods. They're all at your fingertips. And finally, the NUS community is very responsive and ask for help. And I know a lot of people would certainly do their best to help you out. So NUS on solid ground, the benefits are worth it. I do think I spilled over to 1 or 2 more minutes than expected. But with that, I'm going to loop off. I hope that was a helpful foundation. And it's a big pleasure to introduce our next speaker, Frank Delago from NIST and the University of Maryland, and particularly the Institute of Biosciences. And so, Frank, do you want to jump on in?
Yes, splendid. Thank you so much for that really wonderful speed introduction. Every important concept about NUS. I feel like I could kind of walk away now and it wouldn't be such a disappointment for everyone. But anyway, and also thank you to the Ivan folks, especially Krish and Dan Iverson and the MR folks. They are heroes for enabling us to continue to use these fantastic resources and to share how they can be used with the rest of the community. So I'm going to follow up on what Dave has explained to us and talk about NUS in some excruciating detail. And if you care about such things, I'll probably be chatting for 20 or 30 minutes if you want to go off and have a snack instead. Okay, so in an NMR experiment, we have a direct dimension. So somewhere in our pulse sequence is an RF pulse that stimulates the sample, and then we have a radio antenna and we listen to the radio waves that come off the sample. And generally speaking, we use a digitizer that samples these radio waves at uniformly spaced time intervals. So the amount of time it takes to record one of these 1D measurements is basically the duration of time from this first point that we measure to the last point that we measure. In the case of a multi-dimensional experiment, say like a 2-dimensional experiment, somewhere in the pulse sequence, there are a pair of pulses. And the distance and time between these 2 pulses is incremented in a systematic way. And at each one of these different evolution times, we acquire another 1-dimensional spectrum. So our 2-dimensional experiment is a stack of these independent 1D measurements. And the purpose of this second pulse is this pair of pulses is to encode information of interest into the spectral signals. So when we have this two-dimensional data set, if we want to generate a spectrum, we have our stack of time domain measurements, and we can Fourier transform those along the directly detected dimension, and that generates an interferogram. And now we take that interferogram and Fourier transform all of its columns, and that generates a 2D spectrum. Now, because of the fact that we are really measuring a set of 1D experiments on the same sample, the 1D peaks in this directly detected dimension are in the same position everywhere in each one of these measurements. What changes is that their amplitudes are modulated as we go from one 1D slice to another. And so this indirect dimension behaves like a pseudo time dimension. And if we looked at it as a time domain profile, it would look like a time domain signal. So that when we transform it in this indirect dimension, we get something that looks like a spectrum. Now, the amount of time it takes to measure one of these 2D experiments depends on the number of different 1D experiments that we measure to form the indirect dimension. Now, because of the fact that our multidimensional experiments work by taking the signals in a 1D data set and modulating them in the different indirect dimensions, the points that we acquire in a multidimensional NMR experiment are not independent of each other. They have a very special mathematical form. In particular, each individual signal, each multidimensional signal, can be described in terms of a set of 1D profiles. So, for example, let's consider a synthetic 2D time domain signal. The FID would look something like this, and it corresponds to a one-dimensional time domain profile in the directly detected dimension times a one-dimensional profile in this indirect dimension. So this entire 2D matrix that describes one signal is actually completely described by two one-dimensional functions. Okay, so the points in here are not all independent of each other. Now, when we Fourier transform all the rows of this matrix, we get an interferogram, and that property of this interferogram still holds. This 2D matrix is still described in terms of the product of two 1D functions, but now in the directly detected dimension, it's a frequency domain profile and still a time domain profile in this indirect dimension. So now if we Fourier transform all the columns of this to generate a 2D spectrum, again, this 2D matrix, all the points are not independent of each other. This single two-dimensional signal can still be described in terms of these two one-dimensional profiles, and now they're frequency domain line shapes, okay? The Fourier transform that we use to go from one step to another is completely reversible. So the information content in the time domain, the interferogram, and the spectrum is identical, and we can go back and forth at will. Okay, so this point is going to be important. We will raise this point again a little later. Now, in terms of the resolution that we can achieve with a particular measurement, that resolution has to do with the distance in time between the first point that we acquire and the last point that we acquire. And one graphical way to understand this is to compare two different signals that have almost the same frequency. So here's a case where we have two different time domain signals in red and blue, and their corresponding Fourier transform here in red and blue. So over the short duration, these two signals are rather similar and hard to distinguish. But as we acquire more and more points, the differences between these two signals becomes more and more apparent. And that's why the amount of the duration over which we perform this measurement is what determines the achievable resolution. So this leads us to using non-uniform sampling in the indirect dimensions, as Dave has masterfully explained to us. So in this case, in our 2D measurement, we measure a series of 1D spectra, just like we did before, but every so often we skip one of the measurements according to a sampling schedule, a pattern of points to keep or to omit. And this results in a new version of the 2D matrix that takes less time to record because we skipped over some of the 1D measurements that we would normally acquire. The challenge is now that our time domain data now has gaps in this indirect dimension. So we Fourier transform all the rows of this and we generate an interferogram. That's fine. But when we Fourier transform all the columns of this interferogram, those columns have gaps in them. So we get a spectrum, but it's not a great spectrum. A conventional measurement and a conventional Fourier transform will yield the spectrum like this. But if we try to perform a regular Fourier transform on the corresponding non-uniformly sampled data, we get a result that's full of these sampling schedule artifacts, which we don't want. Luckily, there are a dazzling array of reconstruction methods that will enable us to generate an excellent spectrum from this non-uniformly sampled data. And in many cases, if things are selected well, you can generate a spectrum in a reduced amount of time that can be analyzed just as effectively as a fully sampled data set. We'll talk about how we do this and what details you need to consider in order to be able to generate a useful spectrum with your non-uniformly sampled data. Now, in our non-uniformly sampled experiment, as we mentioned, the indirect dimension has gaps in it according to our sampling schedule, the schedule that tells us which points we keep and which points we skip. But even though this data has gaps in it, the duration in time between the first point that we acquire and the last point that we acquire is still as large as it was with the conventional measurement, which means this non-uniformly sampled measurement retains the resolution information that the fully sampled data has. Now we have these missing points in here, and by one method or another, we have to find a way to fill them in. Now, when we have a conventional spectrum with all the points acquired, if we want to process it, one of the steps that we include is to zero fill, append a series of zeros, and then we apply our Fourier transform. But in the case of non-uniformly sampled data, besides the zero filling that we might do, we have these gaps inside. And by one method or another, we have to fill them in, either directly or indirectly. The interesting thing is that almost any mathematical method that we use to fill in points in the interior of the time domain measurement, that is, fill in the points that we skipped in the sampling schedule, we can use these same fill in the blank methods to extrapolate the data in place of the zero filling that we would normally use, okay? And the purpose to that is now we've kind of extended the apparent duration between the first and last point that we have to process, and this will give an improvement in the apparent resolution of the data. So the beauty of these non-uniform sampling reconstruction methods is that we can apply them to non-uniformly sampled data to interpolate, and we can apply them to any data, non-uniformly sampled or conventional, to extrapolate the data as an alternative to extrapolation, say, by linear prediction. And we will see examples of these things. So we will use NUS reconstruction both to fill in the points, interpolate, and to add new points to the data, extrapolate. How does that work? The way to understand how this works is to first understand how the Fourier transform works. And probably most everyone in the audience has seen this before, but we'll go through it quickly. The Fourier transform that we use is the discrete Fourier transform because our data is measured as individual discrete points. And in this Fourier transform, the data that we want to transform, which here is little x of t, gets multiplied by a Fourier term, which has a real part that's a cosine and an imaginary part that's a sine. And so to generate one point in the Fourier transform, big X of f, we take our time domain data, multiply it by a Fourier transform term, and then sum up all the points. So each one of these Fourier terms in the time domain corresponds to a different position in the corresponding frequency domain. So what does that look like? How does that actually work? All of these details are done with complex math, reals and imaginaries, but for simplicity, we're going to look at just the real parts of these operations. So we have some time domain data that we want to transform. We have a given Fourier term. We multiply that Fourier term by our time domain data, and that forms a product, okay? This product has certain amounts of positive intensity and negative intensity. Now, the Fourier transform is a sinusoid, and the signals in our NMR data are also decaying sinusoids. If we multiply two different sinusoids together, the product that we get has exactly balanced amounts of positive intensity and negative intensity. So if we add up all of these intensities, we get something close to zero. So in fact now, as we step through the different Fourier terms, for each Fourier term, we multiply it by our time domain data. That forms a product. We add up all the points in the product to generate one point in the Fourier transform. And it's only in the situations where the frequency of the Fourier term matches one of the frequencies in the time domain data that we get a product that's either predominantly positive or predominantly negative, so that when we add up all the points, we get a peak in the corresponding spectrum. So that's how the Fourier transform works. It's actually pretty easy to understand. Now, in our practical multidimensional measurements, the indirect dimensions can't go on forever. They're truncated. Okay, so we have a sampling schedule that we use conventionally, which is to measure a certain number of points for as long as we can afford, and then we stop the measurement. So this is our conventional, uniformly sampled schedule that's truncated. Now, in non-uniform sampling, we take the number of points that we would have measured conventionally like this, and we spread them over a longer duration. So these two cases acquire the same number of points, but in the NUS schedule, those points are distributed over a longer duration of time. So in both of these cases, when we try to use a regular Fourier transform, when we multiply a Fourier term by our truncated data, we get a truncated product. And because that product is truncated, when we add up all the points, we don't get nice cancellation of the positive and negative intensities the way that we did before. Likewise, for the non-uniformly sampled data, we have our Fourier term multiplied by our non-uniformly sampled data that has these gaps in it. the product has the same gaps in it, so that when we add up all these points, again, we don't have perfect cancellation of positive and negative intensities, so we get a rather strange spectrum. Why do we do this? Well, if we have beautiful, continuous, untruncated data, we get a sharp point. If we have a truncated schedule that's uniformly sampled, we get an artificially broad point and these regular truncation wiggles that we're all familiar with. But if we have our non-uniformly sampled schedule and we try to apply a Fourier transform, we get this nice narrow line the same way we did in this ideal case. And we get a narrow line because the points that we acquire are extended over this whole duration. So the resolution that we can achieve with this sampling schedule is better than the resolution that we can achieve with this sampling schedule. The problem is that this Fourier transform has what appears to be wacky noise in the baseline, but it is not noise. It is another, it's a sampling schedule artifact. So in fact, this is the Fourier transform of the pattern of points that we kept versus the pattern of points that we skipped. And so is this. So the uniformly sampled data has a sampling schedule, and the transform of this sampling schedule, what we call the point spread function, looks like this. So in this truncated data, every peak looks like this and has these regular truncation artifacts, and the size of the peak determines the size of these truncation artifacts. So a big peak will have big versions of these artifacts. A small peak will have correspondingly smaller versions. Likewise, in this non-uniformly sampled schedule, this strange pattern that appears to be noise is the sampling schedule point spread function. Every peak in the spectrum will have this same pattern of transform artifacts. Big peaks will have big versions of this pattern. Small peaks will have correspondingly smaller versions of that pattern. So conventional and NUS sampling schedules and the corresponding transforms and their artifacts. So we'd like to be able to generate a spectrum that has these narrow lines without these noise-like artifacts. How do we do that? We can take advantage of the fact that the size of the artifacts is proportional to the size of the signals. And we do that with a method called iterative soft thresholding, or IST. In this method, we start with a regular Fourier transform of our non-uniformly sampled data, which, as we described, has these crazy looking artifacts, which are a function of the sampling schedule. So we can choose a threshold, which we know in advance is much larger than the largest artifacts that we expect. And we can take some of that intensity off the top of the largest peaks and transfer that into a secondary spectrum. Then we can take the result, inverse transform it back into the time domain, set the parts that were missing in the original sampling schedule back to 0, and Fourier transform it back into the frequency domain again, and choose a new threshold that's a little lower than the one previous. And we can repeat this procedure, each time transferring a bit of intensity off the tops of the peaks into this secondary spectrum. And as we transfer intensity from the original data, because the signals here are getting smaller and smaller, the artifacts get smaller and smaller too. So it's a kind of iterative way to perform the Fourier transform in stages so that we can get a result without the transform artifacts. And it works very well indeed. And we can stop these iterations at any time we want. And if there's any residual here, we can add it into the final IST result to make sure that the result that we get captures all of the intensity that we started with. So this algorithm is easy to perform and easy to understand, and it gives really nice results. These are strips from a 3D, probably, I don't know, CBCANH experiment. But there are several different methods for performing non-uniform sampling reconstruction. And for the vast majority of routine measurements, all of them are very good. So here's uniformly sampled data. Here's what NMR pipes IST looks like. Here's result from Jin-Fai-Ying SMILE, Nesta from the NCI, the original Gangsta HMS IST, and even Maxent from the Roland Toolkit. So in many instances, there are a whole set of different reconstruction methods that we can use to generate a spectrum. But if we want to understand the actual behavior of these NUS reconstructions in a practical way, there are some other things that we have to consider. And this illustration of small molecule NMR with our colleagues at Pfizer is a nice way to understand the circumstance. So in this data that we're going to look at, we have a 2D proton carbon spectrum of a bile acid, UDCA, okay? And in this spectrum, we're going to keep an eye out on this little pair of peaks here that I've drawn in an expansion. This proton carbon experiment was measured with 1,000 increments in the indirect dimension, which takes about 4 hours. So in a pharma company, this means that a measurement like this would be put in an overnight queue, a night queue, so people can't get it back in the same day, which is good, but it's not great, right? So if instead of measuring 1,000 increments in the indirect dimension, we only measure about 128, so I'm using these blue bars to kind of represent the sampling schedule in the indirect dimension. If we measure just 128 increments and reconstruct the spectrum, we get much lower resolution. And in particular, if we look at this, what was a pair of peaks before, it is not really resolved in this case. So we have measurement time of only half an hour, but also the information content of this spectrum is not as good as the one that took 4 hours, okay? No surprise. But what we can do instead is take our sampling, our 128 increments, and spread them out over the same duration as this big fully sampled data set that had 1,000 increments. So here's a kind of uniform random schedule. It takes only half an hour to measure compared to this 4-hour measurement. And in this case, it's reconstructed with IST, and we get beautiful resolution. In fact, even better than this case, because we're extrapolating the data as well as reconstructing it. So this data set, for all intents and purposes, can be analyzed as well as this data set that took 4 hours, except this spectrum can be delivered in the same day, which is a big deal in a pharma company. Now, as we mentioned, there are different kinds of sampling schedules that we can use and different reconstruction methods. So let's look at some differences, okay? So here is the same result reconstructed with SMILE, and it looks beautiful, okay? Here's a different sampling schedule. This sampling schedule samples very densely at the two ends of the spectrum. And again, we get a beautiful result. This sampling schedule is dense only at the start and sparse at the end. But again, the result is pretty beautiful. So all of these cases yield about the same results. The reason is that for this particular data, if we look at a signal in the indirect dimension, it doesn't really decay much, by less than a third. So all the different sampling schedules capture about the same amount of signal. So there's not a huge difference between them. Now, why do we use these different shaped sampling schedules? Well, we can understand that by looking at the point spread function, the Fourier transform of the sampling schedules. And as an example, here are 16 different uniformly random schedules that are Fourier transformed. So uniformly random schedules give uniformly random reconstruction artifacts, which is good. We like that. Now, if we use a different schedule that's weighted at one end or another and look at the Fourier transform of these different schedules, what we see is that the reconstruction artifacts are actually smaller near a given peak, and they get larger as they move out. So an advantage is that if we measure a spectrum where peaks tend to clump together, their mutual reconstruction artifacts will interfere with each other a little bit less. Okay, so this is one way we can gain an advantage from these weighted sampling schedules, but it depends on the fact that peaks tend to be clustered in regions rather than uniformly distributed throughout the spectrum. Now, in all these different cases, different sampling schedules, different reconstruction methods, the peak positions are reproduced perfectly. And this is a general point in NMR. If you know that a peak is there, you can always measure its frequency with pretty good precision. Now, here are the volumes extracted from different peaks in these different cases. And in one of the examples, we extract volumes just from a linear predicted conventional spectrum. And what we see is the extraction of volumes in all of these cases is about as good. And for this example, the main source of error is actually systematic distortions in the measurement itself. So all of these methods are nicely linear and can be used in a quantitative way. But here's the topic that we love. How many increments should we actually measure when we want to perform NUS? Now, as Dave Robniak said, we can talk about coverage or sparsity. We might say, all right, I'm going to measure this NUS experiment with 50% density. But 50% compared to what? 50% based on a spectrum that has 1,000 increments, or 50% based on a spectrum that has 100 increments. So those are all different. How do we determine that? What do we need? Well, the folks like Donahoe, who developed the original compressed sensing methods, have studied what it takes to make a good reconstruction in terms of how many samples you acquire relative to the number of signals that there are to reconstruct. And what they found is that there is an abrupt boundary between the ability to make a good reconstruction and a bad reconstruction. So let's talk about how that works. To understand this, we're going to have a look at this data here. It's proton carbon data. It's simulated. This is simulated to mimic an actual protein, the NOE spectrum from an actual protein called PIN-S. This version of the data has 378 peaks in this proton carbon spectrum. And we're going to take subsets of those peaks. So this case, 180 peaks, 93 peaks, and only 18 peaks. And we will see what the influence of non-uniform sampling is on each of these cases. Okay. So, and in this graph, we're going to plot the deviation in a given reconstruction from the fully sampled version of that data. So this is NUS reconstruction on the fully sampled data set. Here's data at 95% sampling. So everything looks very good, right? 90, 85, 80%, 75, 70%, 65, 60%, 55%, 50%. And in a 2D, we would commonly use 50% sampling density for a case that's routine. Now, when I start to go below 50%, to 45%, and now 40%, and 35%, 30%, now 25%, I can start to see artifacts here in the case with 378 peaks. And at 20%, I see lots of artifacts now, but these other cases are still not bad. At 15%, now I start to see artifacts. In this case, at 10%, I start to see some artifacts here. And at 5%, all three of these cases show substantial artifacts, but the sparse spectrum that only has about 18 peaks is still not so bad. Okay, so the number of samples that we need depends on the complexity of the spectrum. And in a way, that kind of makes sense, right? Because if you think about the most crowded column of the indirect dimension in your spectrum, if that column has 10 peaks in it, you can't reconstruct those peaks with only 10 samples. You have to have enough samples to account for all the signals. And furthermore, if you think about this, what do you need to identify a peak in a spectrum? Well, you need to see the peak, but you also need to see empty space on either side of it. So the number of samples that you measure has to be sufficient not only to identify the peaks, but to account for empty space, the sparsity of the spectrum. And this whole business of non-uniform sampling only works if the data are sparse. In other words, if the spectrum has more empty space than signals. Now, we can think of this in terms of a degrees of freedom argument. In the simplest case, a given peak has a frequency, it has an intensity, it has a line width. So those are three parameters. We can't describe those with just one or two samples. So one way to think about it is, if you had a 2D spectrum that you knew only had one peak in it, how many increments would you need in the indirect dimension to generate a useful spectrum? And it won't surprise you to find out that you have to measure somewhere in the neighborhood of 5 to 15 increments for each signal that there is in the most crowded region to reconstruct. And what we just saw, it illustrates this. And here are the different RMS graphs for these different cases. Okay. So this is how you can determine how many samples you need in your NUS schedule. Okay, and now very quickly, I know I'm a little over, I'm going to return to this point that we talked about, because this will be a topic for the next time we get to speak here at Ivan. So we talked about the fact that a multidimensional data set, the signals in it can be described in terms of 1D profiles. So for example, if we have a measured spectrum, we can describe that spectrum in terms of a collection of individual 2D peak models. So these are modeled peaks here. Here is measured spectral data over here. What this also means is if we have a 3D interferogram, okay, so this is an interferogram in which two of the three dimensions have been transformed. Each of the 2D peaks that we know about modulates along the indirect dimension. So these are the different planes, and you can look at a particular peak and watch it modulate from positive to negative to 0 and back again. Okay. Now, any one of these planes can be decomposed in terms of these known 2D signals. So for example, we have one model peak and another model peak, and we can find the coefficients that when we multiply these two models together and add them together, gives us a model of the corresponding signals in the interferogram. And extracting these values, these intensities, is a linear least squares problem, easily doable with SVD. Now, as we spoke about, the information content in an interferogram is the same as the information content in a spectrum. So if we have decomposed the spectrum in terms of known 2D peak positions, we can also decompose a spectrum in terms of known 2D peak interferograms. So for example, here's an interferogram, only one dimension, only the directly detected dimension transformed from a 3D data set. And what you see here are the individual interferograms of a collection of different 2D peaks. So we can describe this interferogram in terms of this collection of interferograms. And what that lets us do is extract the intensities of each 2D peak on a plane of a 3D measurement without reconstructing the indirect dimensions. And we can do this with conventional data or NUS. And this is what I'll talk about when we visit again next time. So that's the conclusion. NUS gives us a way to use sampling schedules that have different strengths and weaknesses. In particular, we can improve resolution with a given amount of measurement time or retain resolution with a shorter measurement time. And the difference between the NUS schemes and the reconstruction methods are usually not critical except in the extreme circumstances of high dynamic range, high signal complexity, low signal to noise, or very large spectral size. So that is my overview. I hope you liked it. And if any of this content is interesting to you, remember at NIST, we have some awesome postdoctoral opportunities. So lots of folks helped. That's all. And that is my summary. Thank you for being patient.
Thank you, Frank. That was awesome. I love seeing the world of NUS through your eyes, but also the new work is really cool too. Let's see, I was derelict in my duties, and Chad's going to help get me back on my duties because I forgot to remind everybody that Ivan welcomes a conversational environment, and Ivan welcomes anybody to throw a question into the chat. We'll try to make sure that gets seen and heard. And so with that, I see Chad has a question. Jump in.
Yeah, Frank, great talk as usual. I learn something new every time I hear you talk. So this is always a fun time to get together. About a half a dozen slides from the end of your talk, you showed a plot where you went out with NUS, and then the x-axis, I guess, was the number of peaks. And you said it's between 5 and 15 is sort of the number of samples you need per peak.
Right.
What was curious about that plot that I've never noticed before is that it goes down and sort of reaches an optimal, and then it starts to come back up. Do you understand why that is? Yeah,
I think I do. And I don't think you can place too much of an emphasis on that point, and I will try to explain why. Let me share the screen again. Okay, and now, first of all, I will say the caveat of this is that these are relatively low resolution line shapes that don't have any fine structure. Okay, so if you have a complicated line shape that has fine structure, you'll need more samples. And you can go back to that rule of thumb. How many increments would you need for a 1 peak spectrum? And that will give you a guide. Now, what I measure here as a way to show the deviation or the kind of error in a given reconstruction is the difference between a given NUS reconstruction and the ideal reconstruction. Okay, but there is no particular reason why those two should match because they're generated in different ways. Okay, so this figure of merit is only approximate. Now, I'll turn that question around and say, can you think of a reason why this would go down? with numbers of samples. And I don't think that it makes sense that it would. And in fact, it doesn't always. So for some of these cases, it goes up a little bit. For some of these cases, it goes down a little bit. I think that's, it's just in the approximate nature of this figure of merit that we're using here.
Right. And the optimal for that figure of merit is 1, not 0, right? So you don't.
Yes, right.
So in fact, my question was maybe off target, because what's happening first is you're overshooting. It's going below 1,
yeah,
and it comes back to 1. So,
right.
so maybe that's also part of the answer, right?
Yeah, that's a good observation that didn't occur to me.
Cool. Thanks.
I think we could probably squeeze in one more question for Frank before we move on. Sorry, Frank, I cut you off.
Oh, no, it's fine. Thank you. And thanks for your patience. Sorry, I went long. It's my way.
You love it. Okay, I think I don't see anything popping into the chat or other hands raised. So it's a delight to welcome Ben Harding and Chad from the University of Wisconsin, who give us the double meaning of the title of this session, NUS on Solid Ground. So take it away.
Yeah, thanks, Dave and Frank. I'm here just to introduce Ben, and so he's sharing his screen. I'll just take you through the first couple slides by way of introduction, and just wanted to give my regards here from the University of Wisconsin-Madison. Whereas, as I think many of you know, I moved a few years ago upon John Markley's retirement, and along with Katie Hunsrol-Wildman, we direct the NMR FAM now. We've been through a large series of upgrades, and I wanted to thank, please, Ben, go to the next slide, because since 2020, starting in early 2020, that's Kevin Gehring up there in the upper left corner shoveling snow at the loading dock before moving in the first magnets that we brought to NMR FAM with help of the MR Resources crew, John Webb, and you can see in these pictures, David Gardner, and others from MR Resources who helped us get 3 magnets in just before the pandemic. We then moved a wide bore 750 from Urbana, which you can see on the bottom of this slide. On the next slide, Ben can show, I think, a summary of all the magnets we've moved into NMR FAM up till yesterday. And that includes a total of 84.6 Tesla of magnets at field, which used to be in Illinois, which are now in Wisconsin. And so if you have a compass and you're somewhere in northeast Illinois or southeast Wisconsin, it might not accurately read where the North Pole is anymore, because we've moved so many magnets. In any case, we are in the process now, if you go to the next slide, Ben, of moving in a 1.1 gigahertz magnet as part of the network for advanced NMR. That actually came through the roof at NMR FAM yesterday. So we're very busy working with Bruker to install that magnet. We hopefully have it at field operating in a couple months. And so we will, of course, update on that. And that magnet will be called Lockenfelder, in keeping with the history at NMR FAM of naming our magnets after cows, with the number of letters proportional to the number of hundreds of megahertz. Okay. And so with that, I want to hand things over to Ben without taking up too much time. But to point out that following Frank's talk, where Ben will pick up is on those very complex, challenging cases that Frank mentioned at the very end. These are problems involving biological solids, where we have line shapes that are in general not clean Lorentzians. We have many, many peaks in large protein samples. And Ben is going to show some examples of 3D and 4D spectra where we have literally thousands to tens of thousands of peaks, and talk about some of the practical aspects of how to handle that situation. So I'm looking forward to Ben's presentation. I just note also Ben is now a third-year graduate student in my group who started at the height of the pandemic. He did undergraduate research at Miami of Ohio with Gary Lorigan, and also with Ramamurthy at Michigan. So he came in very well prepared, and he's been a real great resource in the group. And so I'll hand it over to him so you can hear more about his work.
Great. Thank you so much, Chad, for that introduction. And it is a pleasure being able to follow Frank's talk. And as Chad mentioned today, I'll be talking about, while I will be talking about some more complicated spectra where we will be seeing tens of thousands of peaks, it's best to approach the analysis from a practical standpoint. So today I'll talk about NUS on Open VNMR-J for biological solid state NMR, and some practical aspects of monitoring 3D and 4D experiments of biological solid state NMR. And I'll just note as well that we do a lot, we reconstruct our NUS spectra using SMILE reconstruction. SMILE was developed by both Frank and Jinfa, primarily because it is faster than other reconstruction techniques, and it's user-friendly in the sense that you can easily integrate it into your NMR pipe processing script. Okay, so let's start off with the example of a carbon-carbon-carbon 3D solid state experiment. Up here is the pulse sequence. So at first we achieve cross-polarization from proton to carbon. We increment along our first indirect dimension, and following that, we have a short DAR mixing period. This is short because we primarily want to identify intra-residue contacts. And following that, we increment along our second indirect dimension, following a longer DAR mixing period. And this recoupling is longer because we wish to identify longer inter-residue contacts. And then finally, we can detect along our directly detected dimension. So if we think about this, how long it would take, we have to account for the number of transients, phases, the time per scan, and how many increments are along both indirect dimensions. So back of the envelope calculation yields that this would take roughly 16 weeks, which is unfeasible. Even if we reduce our phase cycle such that our NT here is now 2 instead of 8 up here, this reduces it by a factor of 4 to 4 weeks, which is a little better, but still remains unfeasible considering our spectrometer, the magnet, needs cryofills every once in a while, so you will need to stop your experiment. However, if we employ non-uniform sampling at 25%, we can reduce this 4 weeks down to 1 week, which is now in the limit of feasibility. So this is an example of a 25% Poisson gap schedule that Dave briefly mentioned at the beginning. Essentially, we've constructed this using Gerhard Wagner's HMS schedule generator on his website, which is here. And some practical considerations when you're constructing your NUS schedule is you have to first, as Frank mentioned, identify your resolution, which is your directly detected dimension. We generally like to detect out to about 1.5 times our T2 for our directly detected dimension, which in this case is 15 milliseconds. And our indirect dimension, we generally sample out to about 8 milliseconds. And in this case, this is 384 by 384 points, which you can see here. And the beauty of that is we are able to use SMILE reconstruction to reconstruct, as Frank beautifully showed in his PowerPoint. We can not only reconstruct those missing points, but we can also extend or extrapolate, as he said, out to about 1.5 times that. So to achieve better resolution in our indirectly detected dimensions. The following examples that I'll show are monitoring the progress of an alpha-synuclein fibril, which is associated with the neurodegenerative disease, Parkinson's disease. So I will be showing an example of a 3D carbon-carbon-carbon experiment of a similar synuclein fibril that Chad's group has determined the structure of back in 2016. So here's a representative plane of a carbon-carbon-carbon 3D of a synuclein fibril. The first DAR mixing is 50 milliseconds, like I said, to identify intra-residue contacts. And the second DAR mixing period is 500 milliseconds to identify these interresidue long-range contacts. If we look at this representative plane, we see all the peaks that lie along this red line are the XY diagonal. This means that the frequencies along this diagonal have equal omega-2 and equal in omega-2 and omega-3. This is not unique to the three, but rather is unique to rather a two-dimensional carbon-carbon spectrum. And the same applies with this. All the peaks that lie along this blue line, or the XZ diagonal, where frequencies 1 and 3 are equal. However, if we turn our attention to the peaks that lie in this green circle, this is the most fruitful information that a carbon-carbon 3D will provide us, because these are all unique peaks. What I mean by that is that omega-1, omega-2, and omega-3 in these cases are not equal to each other. So it's highly encouraged to monitor the progression of these unique peak buildups during a carbon-carbon 3D. Okay, so what we do generally is count our peaks as a function of NUS schedule to monitor the progress. I look at high SNR peaks, and we define these high SNR peaks as peaks that are at least 16 times the noise. And what we see here is we plot the total number of peaks, which are in this this orange reddish curve, and we plot the number of unique peaks as a function of NUS percentage. And interestingly, what we see here is that both curves steadily increase as a function of NUS percentage. And this is as expected. The number of unique, or roughly 35% of the total number of peaks are unique peaks. So that, as seen here. But our next question is what happens as we monitor peaks closer to the noise floor? So now let's look at moderate SNR peaks as a function of NUS percentage. So we do the same thing, only instead of looking at peaks at 16 times sigma, let's look at peaks that are at least 8 times the noise. Interestingly, what we see here, that when we count the total number of peaks, the trend goes down at 5% and steadily increases from roughly 7 to 15%, and then begins to increase or detect more peaks. We're able to count more peaks as a function of NUS percentage after 15%. And when we count the number of unique peaks at 8 times sigma, it steadily increases from 5 to 15% relative to after 15%, where we see a higher peak count concentration per NUS percentage. So this particular trend right here, where it goes down in the total number of peaks, is quite interesting to us, because signal averaging tells us that we should consistently see more and more peaks as a function of time. So we ask why this is the case. And in order to answer this, we slowly creep down even more towards the noise floor and look at low SNR peaks, or peaks that are 6 times the noise. Instead of just 2 curves, we now plot the total number of peaks, which is the blue curve, the total number of positive peaks, which is the orange curve, and then the number of unique peaks, which is the gray curve. When we look at the blue curve here, we see that the expected, as we saw the last slide, the total number of peaks goes down from 5 to roughly 15%, where at 15%, an inflection is observed, and then we start to see more and more peaks as a function of NUS percentage. And interestingly, we see that the total for both the positive peaks and unique peaks, the number of peaks detected as a function of NUS percentage slowly is incremented or slowly increases up from 5 to 15%. And after 15%, we see that all three trajectories increase substantially for the peak count versus percent NUS. So, we interpret this that we need at least 15% NUS for this particular protein in this particular experiment. As it's been emphasized before, you need to be able to understand what in order to choose the correct NUS schedule and what percent you need. It depends on a case-by-case basis. So in this case, we interpret that we need at least 15% to start observing or detecting peaks that are, or I guess, valid peaks. And we attribute this downward trajectory that to reconstruction artifacts due to low sampling density. So we're able to apply this sort of technique to a variety of different proteins, and even in four-dimensional experiments, especially the CAN-COCA, like we have down here with the synuclein fibril, and a CAN-COCX for microcrystalline GB1 up here. And up here, the pulse sequence is shown that's been published by Chad's group since back in 2007. And I'll just the example of the CAN-COCA of the synuclein fibril. In our directly detected dimension, we digitize out to about a little over 15 milliseconds. And for the nitrogen, carbonyl, and C alpha indirect dimensions, we digitize out to about 15, 10, and 7 milliseconds. And we use SMILE reconstruction to reconstruct these non-uniformly sampled spectra. And we can also extend it up to 1.5 times that. And we're able to achieve collect this sort of spectrum in roughly a week of time. We are also able to apply similar procedures to a membrane protein, in this case EMRE, which is an asymmetric homodimer reconstituted into POPC bilayers, and we're able to apply a similar technique to the 3D CAN-CO spectrum we collected. And with that, I would just like to thank everyone who sort of worked on NUS and how we look at the progress of an NUS experiment, and that's our postdoc, Dr. Colin Borsick, and the other graduate students, Moses and Owen, both in the biophysics graduate program, along with me. So with that, I will take any questions, or we can move on to the next speaker.
This is awesome. Thank you so much. Again, we would welcome a pause for any conversation. And I know sometimes folks are a little anxious to interrupt in the middle, but actually you're always welcome to also jump in between presentations too, during presentations with any of your questions. If not, I have a really quick question to kick the ball off.
Sure.
So I love this analysis of number of peaks, and I'm straining to think of an application where somebody has detected so many peaks with NUS. And in terms of this point where, as you get roughly below 15%, you start to see an increase in the number of peaks detected. Just to make sure I'm following, that's essentially you're picking up artifactual peaks at that point, and that's part of why you're defining that cutoff, or did I misunderstand that?
Right. So, yeah, we see this downward trajectory, or the total number of peaks that we see as a function of NUS from 5 to 15% decreases, and that's completely unexpected. Mm-hmm. So once we see that, we have to it's helpful to actually look at your spectra too as a function of NUS. So we have to do that, and we do both of those. We look at the number of peaks we detect and our spectra, and essentially it's a judgment call. But we understand too that with a carbon 3D, as you've said, there are so many cross peaks. So we we intuitively have to keep sampling out to at least 25% in order to essentially find the number. I don't know.
Yeah.
It's sort of a judgment call. Once we see this inflection point, and we look at the number of positive and unique peaks as well, sort of in the similar trajectory, then that intuitively tells us that the peaks that we are detecting are valid peaks, or are actual peaks and not artifacts. That's what this graph here shows us.
Sure. I also wanted to do a follow-up. I noticed the Poisson gap schedules that you showed. If I saw them right, I believe they look like what are sometimes called PG1 schedules. They are dense at the beginning, at the end.
Right.
Did you try any variations like what sometimes people call PG2 Poisson gap samples that are dense at the beginning and less dense at the end?
We did not.
Okay.
No.
Yeah.
We do know that generating sample schedules is an active area of research. So it's sort of hard to find a balance between determining an optimal schedule and for your particular protein in the particular experiment that you want to run. But we're certainly not, we certainly aren't tied to one particular sampling schedule. We're open to working with NUS schedules to just collect spectra with better sensitivity, enhanced sensitivity, certainly. But I will note that this is particularly helpful because the dense sampling schedule down at the lower left emphasizes more sensitivity, right? It's going to give us more signal, whereas, and then the dense sampling towards the top right will enhance our resolution. So I think that's the idea of this particular sampling schedule, which benefits our particular protein and our particular experiment.
Yeah, there's a really nice paper that Adam Schuyler did at UConn that sort of contrasted PG1 and PG2. And I think PG1 ultimately wins in the resolution category, like you said, but I think then PG2 wins in the sensitivity category, so that that dense bit at the beginning does offset some of the sensitivity loss of the dense bit at the end. But ultimately, you'll be facing a sensitivity trade-off. But I certainly understand your rationale here, of course.
Sure.
And again, you're going after an unprecedented number of peaks. You definitely have to think about the compressed sensing theorem at this point.
Right, and I don't think I mentioned it explicitly, but in this last slide here, the number of unique peaks that we've identified are over 30,000 unique cross peaks. So,
wow, that's really cool.
So yeah, optimizing an NUS schedule to accommodate this sort of experiment is certainly non-trivial.
Mm-hmm. Absolutely. This is fantastic work. I think as we look at the clock, I think we should then, in the interest of time, go to Professor Len Mueller from the University of California Riverside, who's going to take us in the direction of some different sampling and processing, but also revisiting something that has come up already. What is the true information content of NUS spectra? So really pleased to have Len Mueller here. So take it away.
Okay, well, thanks to all of you who have stuck around to the end, and thanks to my colleagues for the great introduction and the folks at Ivan. So today I want to tell you about the work we've been doing on non-uniform weighted sampling using what we call consistent RMS noise with some applications to solid state NMR. And to set the stage for this, I'm going to be talking about the dense sampling regime. Situations where sensitivity enhancement is the ultimate goal. And under non-uniform weighted sampling, as Dave mentioned earlier, we're taking multiple samples on the Nyquist grid, but multiple samples at each time point according to some NUS sampling schedule. And I'm going to use these exponentially biased sampling which are characterized by a bias which is basically telling you how much are you pushing those measurements to the early time points. And for all the comparisons that I'm doing, in case I forget to say this later, they're all done with the same number of data points. So if you sum up these sampling schedules, they all come up to the same number. So it's a constant overall 2D or 3D experiment time. And this is sort of a basic question to ask, and I know everyone here already knows the answer to this. It's yes. But how do we understand, in this scheme, what's the increase in sensitivity that we get from these schemes? And I have to admit, actually, that when I first heard about NUS, I was sort of a quiet skeptic, right? It's not that I didn't believe my colleagues who kept telling me how great it was, but it's just recognizing that there's some very non-obvious aspects of signal to noise and data processing that really made me a skeptic about most claims. But what really changed me, what really made me a true believer in NUS was the technique of Monte Carlo statistical analysis. And so I want to talk about this because it will be important later. And so Monte Carlo simulations are a rigorous statistical approach that's particularly useful when comparing techniques in which the noise may be masked by later processing. And this happens all the time in NMR and under NUS processing. And so what we're doing in Monte Carlo is we're going to start with a synthetic signal, and then we're going to add to that noise chosen from a well-characterized distribution, typically Gaussian white noise. And that's going to give us a model signal. And then we can fit that in the time domain, say, to an amplitude, a frequency, and a width, or I can pre-process this. I can Fourier transform it. I can post-process this. I can do NUS reconstruction if I want, and then fit that in the time domain as well to the same parameters, area, width, and frequency. And then I'm just going to repeat this process, 10,000 or 100,000 times. And I'm going to histogram up the results that I get for each of these fits. And then from those, I'm going to extract things like a mean and a standard deviation. And it's a standard deviation, which is the key part, because this is really the uncertainty in our measurement, right? It corresponds really nicely to what we expect an experimental error to mean. It means if I reproduce the experiment exactly, just with different noise, how close do I expect to be to getting that same parameter back? Okay, and then typically we would report this as, say, a coefficient of variation, which is the standard deviation divided by the mean, that's the uncertainty, or the inverse of uncertainty, which is knowledge. So we just invert that. And I'm going to concentrate on knowledge. That's going to be my measurement that we discuss when we're looking at the quality of reconstruction. And so a higher number is better because it's lower uncertainty. Okay, so to use Monte Carlo analysis for non-uniform weighted sampling, what I'm going to do is generate a FID using an exponentially biased sampling schedule for various biases and for various Tmaxes. And then I'm going to add Gaussian white noise, and then I'm going to fit that time domain data to a decaying exponential. And this is something that Frank mentioned earlier, right? Fitting in the time domain is easy for NUS data. It doesn't matter that I have multiple data points here, right? I just fit them all. That doesn't affect my nonlinear least squares fitting, say. So if you can fit in the time domain, there's really no problem with reconstruction ever. Then I'm going to repeat this process, 10,000 times, histogram the results, extract the mean and the standard deviations, and then display the knowledge relative to uniform sampling out to, say, Tmax equals 3T2. And just emphasize this again, no problem fitting in the time domain. And what's nice about this is it really lets us separate what are the benefits of NUS from the problems with the reconstruction. Okay, so perhaps the most relevant parameter for sensitivity is the signal amplitude. And that corresponds to the peak area in the frequency domain and answers that really important question of, is there a peak there or not? It's related to the signal to noise, but they're not exactly the same. And we'll come back to that again. And so what I've plotted here is the knowledge of the amplitude as a function of Tmax for various biases, going from uniform sampling up to a bias of 2. And all these points correspond to equivalent acquisition times. And so clearly NUS is the winner, right? At any Tmax choice, you do better at defining the amplitude by moving to a higher bias. And for each of these different methods, you always do better by front loading the data, right? Putting it as close to the beginning as possible. Because as Dave mentioned, you want to understand what that initial point in your signal is. And I only have one peak here, so that's easy. But of course, if you want to know the peak position or the line width, you can't just put all your measurements at the beginning. In fact, we can look at what the knowledge is, not just for amplitude, but also for position and for width as a function of the biases and Tmax. And you can see that although we do better for amplitude, we do worse for defining the peak position and worse in defining the peak width when we're doing a bias of 2. So there's some trade-off to get the position of the width. We want to get out to 1.5 to 2, T2. And if we sort of want to trade off between getting good sensitivity without throwing out too much information about position and width, then we might go with, say, a bias of 1, what's often called matched NUS. Now, no doubt these profiles will change depending on the sampling schedule, right? If we go to Poisson gap, PG1 or PG2, depending if we put more measurements out here, we can, perhaps boost up the resolution, which to me means our precision in the width, but we'll pay a price by losing some of the amplitude. So there is going to be a trade-off to that. And exactly what that trade-off is, fills volumes of journals. Okay, so yeah, absolutely. But you already knew that we should all be doing NUS. So let me ask a sort of a fun question, though, if you're doing NUWS, right? We have these multiple measurements at each time point. And the question I want to ask is, is it possible to replace these multiple measurements in the NUWS time domain with the single point, at each time point in such a way that my fit and my fit statistics are exactly the same? Okay. Now I could, for instance, sum these points, or I could average them, or maybe I need to do something else. Well, the answer is you actually need to do something else. And so you can do a little math here. I'm not going to go through this, but it's very straightforward. I can just rearrange my chi-squared goodness of fit, which I have for this initial time domain model, to put all those data points into a single function. And when you do this, there's just one unique way to combine that data for single point measurements at each time domain. And that is to construct a signal in which we weight the data points by the square root of the number of measurements. In other words, what I'm going to do is I'm going to sum each of these measurements at each time point, and then I'm going to divide by the square root of the number of points that make up each sum. Okay, this might not seem intuitive, but it does if you actually look at the noise residuals from this new time domain fit to this new signal, because what you find is that these time residuals are now uniformly distributed. That is, at each time point, they're picked from a noise distribution with the same standard deviation. That is not true if you take the average of these time points. They'd actually be growing with time, or if you take the sum, they would be decaying with time, okay? And so this is what we call using consistent RMS noise. Now, when we do this, the signal is going to be decaying because of that weighting, which for an exponential weighting at T-samp, it's actually the square root of that. So it has this extra decay rate, 1/2 T-samp. And again, this sort of weighting is distinct from apodization weighting or from just using the sum as was done for traditional NUWS. Okay, now why do we want to do this? Of course, because now we can just Fourier transform, right? I've got single points on a Nyquist grid. I can just Fourier transform then to get my spectrum. And for all the great properties that Dave mentioned about the Fourier transform, right? This is spectacular because I know the information content here is precisely the same as here. And this was constructed to be precisely the information that was in this NUWS signal. So this is the spectrum of this NUWS time domain signal. And we can do Monte Carlo simulations, again, comparing that time domain fit for NUWS with this frequency domain spectrum that we acquired or that we constructed using NUWS UCR, and they are precisely the same. Okay, so let me stress this again. This spectrum is exactly the Fourier transform of this non-uniform weighted signal. It fully preserves the knowledge in going from the time domain to the frequency domain. And this makes it a great fundamental test bed for theory and non-uniform sampling, because if it's true here in the time domain, it's going to be true here in the frequency domain. So all those questions about amplitude and resolution, we can answer those looking at spectra like this. And if we're lucky enough that we can acquire data in this dense sampling regime, we know how to precisely reconstruct it. We don't need to use any other method. We just construct this time domain signal and Fourier transform it. Okay, so for example, we can examine signal to noise under NUS, so not just knowledge of the amplitude, but what the signal noise is. And we can see, yes, indeed, when we go from uniform to NUWS, there's an increase in signal to noise. And if we match these appropriately with a matched filter, now sort of matched to the appropriate decay, which has that extra 1/2 T-samp, we see that we can get, the largest signal noise, in this case, twice of where we started. But we do pay a price, right? You can see the lines get broader. So we are, losing resolution in this process, and that loss is real. Okay, so we can also just calculate how this signal to noise ratio and resolution change under NUS for various biases and Tmax. And what we see, again, is that the sensitivity, that is the signal noise, at any Tmax increases with bias, but it does decrease with Tmax, and these plateau after a while. On the other hand, resolution measured as one of the line width decreases with bias. So we increase bias, we increase the line width, and it increases with Tmax, again, before reaching a constant value. Now, both of these were calculated with a match filter to the effective decay rate, 1/T2 plus 1/2 T-samp. And this appears to contradict the NUS sensitivity theorem, that beautiful work from Dave's group. But note that we're making different assumptions than Dave did in that work. For instance, we're assuming that we have a constant number of indirect points, so all constant time experiments, where I believe in Dave's JPCB paper, they were assuming that they were adding linearly in time as they were going out in Tmax. So there's some different assumptions there. Okay, what does this look like in practice? So here we're going to be looking at a microcrystalline sample of Toho-1 beta-lactamase using 3D NCA-CO correlation spectroscopy with plug for some of our earlier work on low-bashed homonuclear decoupling, where we're decoupling the CA-CO J coupling during acquisition, which gives us that last little bit of resolution because we can knock out that J coupling. And we're going to be looking at 2D NUWS schedules for 3D NCA-CO correlation experiments. I'm showing them here. Here's some of the numbers for these acquisitions. So you can see we're changing the bias from 0 to 1 in both dimensions to 2 in both dimensions. And we're shortening the Tmax. And Tmax is always going to be set to 1.5 T2 effective in each dimension. And that T2 effective has that sampling time in it as well. Okay, and then we process the data in NMR pipe. So thanks, Frank, for creating a new square root option for us for combining redundant increments for the uniform consistent RMS noise. And then we process them with either a matched filter to the effective decay rate or no filter. And then we import the data, the 3D data sets into Mathematica and use a little script to calculate the signal to noise for a given peak. And so first, the good news, right? we see a steady progression in the signal to noise ratio as we go from a bias of, from uniform sampling to a bias of 1 to a bias of 2. And that's exactly what you would predict from theory. Okay, but now the not so good news, this is what happens to the resolution when you have 2 indirect dimensions of NUS. So here we're looking at the 2 indirect NUS dimensions. So we're taking planes in the directly acquired dimension. And you can see that, we start to lose resolution, sizably. And this is just a small fragment of some of the most congested areas of those planes. And indeed, it's really just, the fact that this additional decay because of the 2T samp, when I get to bias 2, that just doubled my line width, and double the line width in 2 indirect dimensions. And, your 600 becomes 300. And so you really start to lose resolution in that case. But, once you have the data, you're free to process it however you want. So maybe putting this matched filter on is, not the best idea if I want to keep my resolution around. And so we can process the data that way as well. When we do that, right, we're no longer matching the filter. So we're not going to get as high of signal noise, but it does help us start to recover at least some of that resolution. So for instance, with bias 1, if you do that, don't put on the exponential filter, your signal noise is exactly the same as what you'd get for a matched uniform sampling bias, uniform sampling. And you recover essentially all of that lost resolution. And for bias 2, you almost do as well. In principle, you should recover it, except for now we're truncated. We didn't make it out to 1.5 T2 effective anymore because we're not putting on that filter. So we, have a little bit of loss from the truncation. Maybe some linear prediction would help us to recover some of that as well. So because we have the data, we might as well just process it 2 different ways. And that's really what we would recommend and what we're doing now when we're processing our data. So, so you process it both ways. When you need the sensitivity, you're looking at this spectrum. When you need the resolution, you're looking at that spectrum. So we would recommend, even if you're very conservative about how you want to do your 3D spectroscopy, there's really no reason not to do this with a bias of 1. You can always recover the resolution when you need it, and you get a little boost in sensitivity when you need it. So, you can have your cake and eat it too. And if you want to be more aggressive, go with bias 2, because you can still recover most of the resolution, but you get this, whopping factor of 2 in signal to noise ratio. So that's really our recommendation of a nice place to work for sensitivity gains. Okay, so to wrap this up, for NUWS, the correct way to combine the data is using consistent RMS noise. That is, you weight it by the square root of the number of data points at each time domain point. And then that spectrum that you generate, and I showed it with exponential, sample schedules, but you could do that with any of them. But that spectrum that you would then generate from the Fourier transform is the full and faithful reconstruction of the time domain signal. NUWS UCR with a bias 1 or 2 offers increased sensitivity with only a modest loss in resolution, and you can easily process this in NMR pipe. So thanks again, Frank, for helping us with that. I hope I've also convinced you that Monte Carlo simulations are a very robust method for assessing the efficacy of data processing in NMR and with NUS. And I'd like to suggest that it really should be the gold standard. If someone makes a claim about what NUS can do or whatever, their new acquisition approach, they really should show that using Monte Carlo, because you can find in Monte Carlo, starting with a time domain signal and then put it through the whole process and show at the end how good and how reproducible that technique really is. And so although I talked about the dense sampling regime, there's actually some pretty interesting implications, even for sparse sampling with different reconstruction protocols, because what's true here is also going to be true there. So if you just dense up those sampling schedules, bring them to this regime where you can actually look at the Fourier transforms, I think some of the claims that we make in NUS processing, can be tested. Okay, and with that, let me just thank the folks who have worked on this very hard over the last few months, especially. So Dave and Manpreet and Chris, as well as the rest of my collaborators, and I'd be really happy to answer any questions. Thanks.
This is awesome. Yeah, thank you. Again, we warmly invite questions, and I think I see Ben up there. Jump in.
That was really cool, Len. Thank you.
Thanks.
I'm really excited to incorporate this and try it out. Just a comment too, depending on how thermostable your protein is, like Toho, perhaps you could even play around with these experimental variables that affect your resolution and sensitivity. So for example, my first thought is, higher temperatures are usually proportional to your resolution, right? So if you go up in generally, so maybe if you push the limits of the temperature, then maybe you could employ a bias 2 schedule to get maybe the benefits of both resolution and your sensitivity. Is that wrong, or what are your thoughts?
Yeah, so lots of good points to your question, actually. So the first is, this is really a nice thermostable protein. You'll note that we probably did not take out the resolution in C alpha as far as we could, for instance. We did that because these were already, so 3D with even, with this well-sampled NUS, it was still, 18 hours, and we had a bunch of these we wanted to test back to back, but we could knock out the CACO coupling and the CA dimension, get the resolution up there. And then we could start to look at some of these other schedules, right, that push resolution near the end, because we're only at 1.5 T2, right? You're still in a regime that if you sample more there, you boost the intensity at that point. You're not going to get as much sensitivity overall, but you could, in principle, increase resolution. It's sort of akin to putting on a rising exponential in data processing, right? You can get a better resolution, maybe, but you pay a huge price in signal to noise. The thing about NUS, when you do that in a sampling schedule, it's real, right? It's not just a post-processing bit. You're actually doing, having more measurements there. So you could play around with that, and that would be interesting to try. We're sort of in the sensitivity limited regime still, right? Our data is good, but we're talking about signal noise of 20 to 1, right? We're not in 200 to 1. So
right, yeah,
we have to be pretty careful about how we go at it.
Right, yeah, you're absolutely right. Some samples are hurting for resolution, some are hurting for sensitivity. So
we want both.
Sample dependent. Yeah.
Clearly we want both, though.
Right.
Actually, Dave, if I can jump in with a question, I just wanted to come back to Frank and Dave both, and maybe Len as well, whoever wants to answer the question. Like, we are still not in agreement as a community as to how to define the sampling schedule. I think Len's work is a really nice step in that direction. But, and honestly, when Ben and I went to the HMS IST website, we downloaded a schedule, and only retrospectively after we did the experiment did we realize it wasn't the optimal one, or could have been better, right? So, I mean, the community standards for selecting schedules are still lacking. Is that a fair statement? And then what should we be doing about this?
Well, I'll jump in with a comment, which is, irrespective of what standards and rules of thumb that we might suggest, as we've discussed today, the requirements depend very much on the nature of the data. How many peaks there are, how they are distributed in the spectrum, whether or not the peaks have fine structure that you care about. So I would argue that the best way to approach this problem is to take your conventionally measured spectra and resample them as non-uniformly sampled spectra. And we've arranged software that makes this very easy to do interactively.
If I could jump in just to add to that, I mean, part of the problem, Chad, is you can change resolution while processing, right? So what do we mean by resolution, right? In the example we showed, we could give up signal noise to get some extra resolution. There's only a few stationary points. And so we should be careful to perhaps define things relative to that. One stationary point is maximum signal to noise, right? That's if you change your processing and, for instance, if you have an exponential weighting, there is one point where you're at the top of that curve. And so that at least is stationary. And that one would have, in uniformly sampled, that would be when your match filter is, exactly matched to your line width. So if you think about metrics like that, perhaps that could be useful because you could back off from that, right? You can pull off the match filter, get better resolution from that in your spectrum, but there's an inherent resolution in your data. And I would claim that's what you get from the time domain fit with proper statistical analysis of the error in the line width for that processing. So that's part of why I'm so excited about what Frank's doing with time domain fitting, right? Because that's irrespective of how you reconstruct. And you'll be able to put error bars on that. You'll be able to put error bars on how well separated your knowledge of two peaks are and what their widths are. So I think that's where the ultimate analysis take place. So just some thoughts on that.
Thanks very much, Frank and Len. And I'm sorry, everyone. Thank you, everyone. I have to jump off, but Ben can help answer remaining questions from our end, or let me know, and I'd be happy to answer emails about it. All right. Thank you.
Bye.
Are there more questions?
Yeah.
This is Krish.
Yep. Any more questions? Sounds like there are not. Somebody say something. Okay. So if that's the case, then we should end the meeting then. And so with that, I'd like to thank everyone for a great meeting, and we'll end with a lot of insights about NUS. And so thanks, everyone.
Thank you.
Bye, everyone. Thank you.
Thanks.
Yeah.